Hello and welcome to this video about my 3D for spatial computing project. Today, when we are working with 3D programs like Rhino, SolidWorks or Blender, we use two-dimensional flat monitors or normal computers. So even if the content that we are viewing has 3 dimensions, we view it in a 2-dimensional format. Spatial computing allows us to view digital elements with depth and volume as if they were actually there. This type of interface gives us a lot more information of surfaces, volumes, and scale that just isn't possible to communicate with normal monitors. And this makes this technology extremely interesting for people like designers, architects, and engineers that work with digital 3D objects that will later become real physical objects. This project is about the opportunities and challenges of designing 3D programs for a spatial operating system. Chapter 1. Windows. It may seem like an assumption to say that Windows will still exist in a spatial operating system, and that's because it kind of is. Windows do allow users to organize all their stuff in front of them in a very flexible and natural way. Windows in a spatial operating system does not have to be like Windows in a 2-dimensional operating system at all, but there has to be probably some type of window-like mechanic that clumps the UI together and defines how they're placed around you. And if that's the case, our 3D apps have to exist in that space as well, in one way or another. When we are working with 3D apps, we almost always are using other apps at the same time. We find reference images on the web, we're looking at a tutorial on YouTube, we're having a digital meeting with a colleague. Windows enables these types of multitasking in a really natural way. And so there was a lot of motivation to see how good a 3D app could be in this space. Currently, the 3D app you are seeing in front of you is behaving very similar to how it would do on a 2-dimensional monitor. It's just a flat projection of a 3D scene. This is probably how you're used to experiencing 3D programs today. But what if we want to get a better feeling for what this car actually looks like? How do the surfaces go and how big is it really? Chapter 2. Surround mode. As you can see, this is only a flat projection of a 3D scene, but see what happens when I click this button. Not only does the app expand into the surrounding of my workspace, making it possible to see a lot more of my 3D scene. The scene itself is no longer a flat projection, but rather a fully stereoscopic 3-dimensional scene. I can get a better understanding of my models in a way that just isn't possible on a 2-dimensional monitor. The surfaces are clearly communicated and the scale is 1-to-1 with real life. Also, I can still use my cursor to click and drag objects in the scene, very similar to how you're used to doing it already. There are some really big drawbacks and difficulties to an experience like this, and I will talk more about that later, but before we do that, I want to show you another aspect of this concept I found really interesting. As you can see, I still have all of my other apps right where I left them, so there's no change to the UI in that sense between the 2 different modes. This makes it very easy for users to jump in between them while still having all of their parallel windows easily accessible and consistent. And this is also true for the 3D app itself. The panels don't change or jump anywhere, they just stay where they are so you know where you have them. You may have noticed that the border of the window is still present, and that's because of a couple of reasons. First of all, even though the app visually bleeds out into the rest of the surrounding, it seems to be a good idea to constrain the actual interactions to the window to maintain some order of the workspace. It's not impossible that you should be able to, for example, select something all the way over here, but my feeling right now is that it feels a bit weird and maybe even a bit chaotic. In the 3D app, you also need to communicate what is forward, so that zooming and orbiting and all of that behaves as expected. And the window border indicates that very well. And then finally, all the panels, the window bar, and everything that's connected to an app is structured around the window in my concept. So keeping the border keeps that structure nicely and makes all of the interaction and behavior of the system consistent between the 2 different modes. So all of that is why I think keeping the window border actually works out quite nicely. In this surround mode, I have also decided to make the 3D objects visible only when they are in front of you. You can see here that once the objects are too much to the side, it fades away. The reason for that is, with this type of navigation where you are orbiting, panning and zooming, looking to the sides while you're moving the camera gets a bit nauseating. And there's really no point in having a full 360 field of view here anyway, because when you're orbiting, the horizon will not stay flat and your distance to the ground will not be consistent. So you will never really feel like you're actually there anyway. The purpose of this surround mode, where everything is truly three-dimensional, is really only about getting a good understanding of form and not about being fully immersed. That's something that spatial computing can also do, but it's a completely different experience. In an experience like that, you would navigate in a different way and you wouldn't have all the other apps visible like this, because they take you completely out of the immersion. That type of experience, I think, is really interesting for architects, for example, because my feeling is that they could really benefit from that fully immersive experience when you feel like you have been teleported into another place. The reason I haven't worked on that is because I imagine it would be very similar to how VR games are made. All of the problems with how you reduce nausea and how you rotate the character without it feeling weird should be the same. People have already worked a lot on those types of experiences. So if I were to add anything to that, I would have to spend a lot of time on it, and I just haven't done that. I had an idea early in the project that the window should be like a window in real life, that you're not looking at, but you're rather looking through. And on the other side would be the scene, truly 3D with proper scale and everything. So almost like a portal that you're looking into another world with. And I used to really like that idea. I thought it was nice that you can get the attributes of true 3D while still containing the app to its window. The problem with that idea was that the size of the window now decides the field of view into the other scene. And so I find myself scaling the window up a lot. Not because I wanted to interact with that extra space, but just because I wanted to see my scene more clearly. And two things happened then. One, all the other apps that you want to use in parallel is pushed to the sides, which is not great because you have to rotate your head more. And two, the 3D window is so large now and it takes up so much space of your field of view. It adds almost no value that it's in a window anymore. At that point, it just makes more sense to allow it to take over all of your surrounding. And that leads us to these two different modes. There's the window mode, where the 3D app, it's just a flat projection of the scene, like on 2D monitors today. And then there's the surround mode, where the scene not only fills up your surrounding, it also becomes truly three-dimensional. Chapter 3. Panels. In a spatial operating system, the UI is not limited to a physical monitor, and so we have the opportunity to explore how we could organize panels differently than we do on normal computers. When inserting the UI from a program like Blender or Rhino into this prototype, it feels a bit strange and not optimized for this format. One thing I've noticed is that I tend to enlarge the window of this program quite a bit in a way I wouldn't do or can't do on a two-dimensional monitor. What happens then with the panels if they are aligned to the border of the window is that they're pushed to the sides and all of a sudden they're facing the wrong direction. And they're doing this in a way that makes it very awkward to use. After playing around in Figma a bit, I had some ideas of what could be interesting. I thought it would be nice having the panels being independent from the window border and having them being able to break loose from the window itself. I did so that they would slide across the surface of the window if they were close to it, but once you drag the panel away, it starts to move independently, similar to windows themselves. Some things felt nice about this, but some things didn't really work. The biggest issue was that I didn't actually get rid of the problem that I mentioned earlier about panels facing the wrong direction once the window is large. So I tried to make all the panels face the user as if they were their own windows. And this works, but there were some new needs that arose. If the panels are rotated independently, it gets hard to organize them and align them to each other nicely as they increase in quantity. So there was a need to group them together to create clusters of panels instead of a large quantity of small independent panels. I did play around a bit with what the rules would be for how panel grouping and panel snapping should behave. Figuring out how this would work in reality would be a project that can take many months, so I haven't done that, but I wanted to explore it a bit to get a basic feel for how it would take form later on, so that I can easier understand how the general experience of a windowed 3D program would be, and then understand the benefits and drawbacks of a system like that. Here's an example of how the user can group panels themselves. There was a need to have the panels stuck to the parent window somehow, so when I move the window, the panels move as well. If the panels were too far away from the parent window, a range of problems arose. The lack of proximity makes it feel very strange that their movements are linked. That's a big one, but another thing is that if you have a lot of panels on a line and you move the window upwards, the panels connected to this window will rotate on the same axis as you would expect. The further the panels are from the window, the less they move because they get closer and closer to the rotational axis. You could rotate them all independently, but then they would start to collide with each other as they go closer and closer towards a point above the user. This could also be solved by making them separate from each other horizontally, but then they would move further and further back behind you until you can't see them anymore. And this effect that you're seeing is still happening if the panels are close to the window, but it happens on a degree where it's not a huge problem as far as I can tell. Anyways, I made sure that the panels parented to the window can't go too far away. It's visually connected with a leash that pulls the panels back if moved too far away. Leash is probably not the best name for it, but that's what I'm calling it now. Adding more panels to my 3D app, I found a scenario where you want to have multiple panels or panel groups from the same app on a line around you. And also there are scenarios where you want the panels to be far away and completely independent from the parent window, even if they are technically part of the same app. So I decided to add a small button that disconnects the panel from the window. They no longer follow the movement of the window, and they can be moved around freely without any limitations. When you attach the panel to the window again, they move back. Another thing to think about is what the panels should be rotated relative to. One option is to have them always perfectly rotated facing the user at all times like this. And the other option is to rotate them relative to the parent window, meaning if we move the window, the rotation of the panels adjusts so that their relationship with the parent window stays the same, but they will not perfectly be rotated for the user. You can see what that looks like here. Relative to the window versus relative to the user. The benefit of having it relative to the user is that they're always facing the user nicely. The problem is that if you're moving the parent window, they easily start to collide with each other. The way their rotation is defined is just very unstable. If you make them rotated relative to the window, they behave in a very stable and predictable way, but in some situations you have to roll your head a bit. I found that the best option is to have them relative to the window when they are leashed, but rotated relative to the user when they are free floating. I can also mention the shape of the window itself does not have to be a rectangle. I have played around a little bit with it, and I think there's interesting stuff to explore, but it's not really what this project is about. But it's good to think about when you're seeing all of this. This project is really about the mechanics of a system like this, and so the visual design right now is just really an example. The leash is another example of things where the visuals are deeply unexplored. It doesn't have to be like this ribbon at all. It could be like a large blob that contains all of the panels, or some particle system that gets more intense when you pull the panels too far away. It could be anything. So just keep that in mind. Chapter 4, Flat 3D versus True 3D. You might think to yourself, if you're in a spatial operating system, why not always use True 3D? Why ever use the version of a 3D app that's just a flat projection of a 3D scene? It turns out there's a ton of problems with working with a truly stereoscopic 3-dimensional scene. Here are 5 bigger things that I've noticed so far. 1. When you move your head, even if it's just a little bit, there's a perspective shift that causes a type of instability of the cursor. On a flat monitor, the cursor is super stable and predictable, but in a system like this, where you're pointing at things at different distances, it's not only the cursor that decides what you are pointing at, but it's also the perspective of the camera or the user's head. This problem seems to be more prominent when what you're working on is closer to you, because the perspective shift is larger. But even when you're working on things further back, it definitely still affects the user interaction in some negative way. You may think that's only because of the way that I've implemented the cursor, but I actually spent quite some time early in the project developing a cursor that's not too bad. There are people who have worked on this problem a lot more than me, of course, and I'm not claiming that my cursor is perfect by any stretch of the imagination. It's just not really what this project is about, but my feeling is that regardless, the cursor in a system like this is not going to be quite as good as the cursor on a flat monitor. 2. We need to define a volume of space where we allow the 3D objects to be. In a system like this, where there are other apps open at the same time as the 3D scene, you can imagine that there's problems with clipping. The 3D objects will invade your workspace and get in the way of interacting with other apps. How annoying would it be if you can't stop your music because there's some 3D model in the way? I decided that the interaction of the 3D scene should be secondary and that the windows and the panels from all the apps should be primary. I had an idea that you would still allow 3D objects in your workspace, but that their opacity would go down and that the cursor would ignore them. But it still got visually quite chaotic, and I didn't really feel like it added a lot of value to let them do that anyway. I found it's much better to make the window itself the near clipping plane. Or in other words, all the 3D objects that come closer than the window should become invisible. When it comes to the far clipping plane, I haven't noticed that there's any difference here compared to 3D programs on normal monitors. I don't see any clear reasons why you would make the far clipping plane not infinite, other than performance reasons, of course. 3. Another problem related to this is zooming. It seems to me that there are 2 ways of zooming here. One would be moving the scene closer or further away, and the other would be scaling the entire scene up or down. I found that you primarily want to zoom by moving the scene, but this is not always possible. Some objects or details are just too small. If you're modeling a pair of AirPods, it doesn't matter how close you move it, it's just too small to keep scale 1:1. And with the near clipping plane as the window, the limitation of how close you can move something before it disappears is actually pretty rough. It happens really early. So zooming has to be a combination of moving and scaling the scene. I currently don't really see how you can get around this. How you implement this is of course something that needs to be worked on a lot. But I have come up with one concept that I think works surprisingly well. I'm aware it will be impossible for you to evaluate how this feels from a 2-dimensional video like the one you're watching right now, but I'd still like to show you an example of how this could be solved. In a program where you're orbiting, panning, and zooming, you have a point in space in front of the user that the camera orbits around, and we can call it the center of orbit. When the user is scrolling or zooming, the system moves everything towards or away from the user. This is true only until the center of orbit comes too close to the window. We have to define how close we let the center of orbit come, so we can create a value that we call d, and that will be the limiting distance. In my prototype, the distance between the user or the user origin and the window is 1.2 meters, so it's not too far away. Here I found a good value for this distance d to be 1 meter. If I zoom too much, so the center of orbit comes closer than distance d, the scene will no longer move towards me, and instead it will start scaling. So everything will become bigger. And then when you're scaling everything down again until it reaches its original size, you automatically go back to moving the scene. When the scene becomes significantly bigger than what you started with, you do clearly notice it. But every step is so gradual that at least I cannot really tell when the shift happens. So there's a surprisingly smooth transition here. Now, this solution, it prioritizes an unobtrusive experience but the scale of the scene becomes a bit ambiguous. The system sort of adjusts the scale automatically, which makes this experience quite smooth, but if scale is important, this may be a bit annoying, even if you clearly communicate what's going on. So this is certainly not a perfect solution, but it's one example of a direction that you could go to solve zooming with a spatial 3D program. The takeaway here is that you could probably make something that works okay, but the zooming will never be quite as simple as on a flat 3D program. The problems with zooming, it also depends on how big the models you are working on are. I tried to put models of a couple of different sizes into my prototype. One pair of AirPods, one car, and then 3 arenas. One arena with a scale 1 to 100, one with 1 to 10, and then finally 1 to 1. I didn't really feel like you ever wanted to scale them down, which I thought was interesting. Navigating around and inside the 1-to-1 arena was for me a really incredible experience. The main scenario where it might be interesting to scale objects down here is if you're collaborating with others. Then you probably want to sit around a model so it's easier to point and talk about stuff, which would be difficult to do if you are working, for example, on the arena that's like 1-to-1 scale or other extremely large objects. The car felt like a great size to work with. Very large objects like the arena can sometimes feel a bit flat, just like in real life actually. While the car is small enough so the perspective makes the surfaces and the volumes very clear, it's also big enough so you rarely have to scale it. With the AirPods, you always have to work with it scaled up because they are so small, and then you do lose one of the big benefits of using spatial computing, which is accurate scale. But you still get a really good feeling of how the surfaces and the volumes are, and that still makes it very beneficial to use spatial computing. 4. Another thing I've noticed is how tiring it is to constantly switch between looking far away and shifting to windows and panels which are much closer. It just feels more comfortable looking at something flat in a spatial interface. I suspect it has partly to do with the fact that spatial computing does not have depth of field yet. I read somewhere that the brain uses multiple cues to determine how close something is. One of them is triangulation with our 2 eyes, which we do get here, but also with the depth of field. And that has nothing to do with the fact that we see in stereo. In real life, each eye has its own depth of field, just like a camera. But with spatial computing, there's none. The brain gets less cues and has to do more work. Now, that's just an hypothesis, but either way, looking at a flat app is way more comfortable than looking at a truly 3-dimensional scene. 5. The last big problem I want to talk about is box selection. Box selection is one of those super common mechanics that you use all the time in 3D programs. How well you do this, I think actually has a serious impact on the overall use case of working with 3D in a spatial operating system. And that's why I wanted to go in and explore it a bit to see how big of a problem this is. In a flat 3D program, box selection is really a simple thing. You just draw a box and everything within the box is selected. In a spatial 3D program, it gets a bit chaotic because then you would no longer select an area, but rather a volume. You can imagine that you draw a box that's infinitely far away. The volume between that box and the eyes of the user becomes like a pyramid shape, which defines the volume that we want to select. Another way of explaining this would be to say that you're actually selecting a part of your field of view. One of the problems here is that you have 2 eyes that are looking from this at a slightly different point. From the perspective of one eye, it will look like you are selecting a little bit less than you actually are. And from the perspective of the other eye, it will look like you're selecting a little bit more. You can communicate what is being selected more clearly by making everything not selected getting darker and then keeping everything you are about to select lit up. And this helps a lot, but there is another huge problem. And that is if you move your head, the entire pyramid is getting like tweaked. So you're actually changing the volume that you are selecting dynamically with your head movement. And this is awful. it just doesn't work that well. Now, I have not worked on this enough to know how this will turn out in the end. Either you can make this work good enough in some way, or you can come up with a different way of selecting volumes of your scene that makes sense. But it's just a very difficult problem because you don't have control over how far away the cursor is, just which direction it's pointing. The 3D scene, it's also too far away to use any type of hand tracking or anything like that. So it's just a really difficult problem. What you should take away from that and all of the other things that I mentioned is that the interaction of flat 3D programs is just going to be a lot simpler and easier to use than a true 3D program in spatial computing. There's a lot to figure out for this to become viable as a real product, but I really think it can be good enough to justify the use case. The benefit of observing models and scenes that's truly three-dimensional, where you can get a fantastic feeling for surfaces and volumes, is so great that even if the interaction is worse than on a flat 3D program, you'd still think the overall experience is better. But my final conclusion is this. If the end result is going to be something that's two-dimensional, like a movie or a game meant to be consumed on a normal monitor, it makes very little sense to do the work in a truly three-dimensional spatial lab. And last chapter, chapter 5. Some things you may be wondering about. You may wonder why I choose to say spatial computing instead of virtual or mixed reality. Both VR and MR have some associations with it that this project isn't really about. The system I imagine does not have to be a completely virtual. It can have pass-through, where you can also see the real environment you're sitting in, or not. It can be either. What's interesting for me is the truly three-dimensional interface that the headset can give you. Spatial computing is just a word that describes the general technology I'm focusing on really well, without any misleading associations. So that's why I choose that word. I also want to mention why I use keyboard and mouse as input controllers, as I know people will wonder about that. When people think about this type of spatial interface, they probably have an idea that you would manipulate the digital objects with your hands, similar to real life, or with some novel controllers. Handheld controllers have some awesome benefits for some types of experiences, and of course it feels amazing to just skip controllers completely and just do hand tracking. The problem is that these input methods, they're just not accurate enough to work with in a comfortable way. It's kind of like the same situation as touch versus keyboard and mouse. Touchscreens are great for some types of devices, but we all understand why we prefer to use keyboard and mouse when we are using spreadsheets or writing documents. The keyboard allows for fast text input, and the mouse is just really good at pointing at stuff with, which is what we want from almost all types of work, even in a spatial operating system. This does not mean that, for example, hand tracking should never be used, but they're not going to be the main input method. I should also mention that even though keyboard and mouse are my main input method, the way they are visually implemented in my prototype is not how I imagine it to be in the end. Here it looks a bit wonky with these floating hands, but other people have been working and will be working on that a lot, so it's just not really what this project is about. So this is what you'll get for now. And that was what I wanted to show you today about my 3D for spatial computing project. I don't really have anything else to say other than a quick thank you to my mentor for this project, Matteus Krenn. Not only did the project become so much more than it ever would have been otherwise, I also walked away from this 10 times as good of a designer as I used to be. It's been really incredible, and I'm very grateful for that. And also thank you for watching this video. It's been a lot, but I hope you enjoyed it. Have a great rest of the day, and I'll see you in the next one.